my watch and my laptop disagree with that clock, so I'm just going by these two that agree. So actually, voting on the correct answers is actually a concept that I will talk about in parallel computing later, too. So, okay, close enough. So welcome back to Lecture 3, which is on parallel machines and programming models. And I just want to review how far we got last time. But before we start, are there any questions? I already had one about the homework that hasn't been posted yet. But I mean, if there are any other questions, we're happy to go on to them. There was a question about office hours of one of the teaching assistants, and we'll do a little interrupt in the middle as I switch from Lecture 3 to Lecture 4 so that Aditya can answer that and any other questions. So anyway, the goal of this lecture is to tell you about parallel programming models and the machine models that go along with them. So the three questions that we want to answer, or that you should always ask yourself when you're confronted with a new machine or a new programming model, are how do I express control? You know, how do I say, please do all these things in parallel, and in what order they should be done? And all of these have different ways of expressing that. The other question you always have to answer is about the data. You have to be able to distinguish between which data is private to one particular sequential looking piece of code you may write. So you have a loop from I equals 1 to 10. You'd like I to be yours, nobody else gets to change it, as opposed to an array, which maybe everybody can refer to. And these different programming models have different ways to refer to shared and private data. And so last time it was shared, and now it's going to be and so now nothing's going to be shared. That's the next model we're going to do. And the other thing that all of these have to give you an ability to express is synchronization. How do you get two different processes that are running in parallel to coordinate and share data so they can agree on the answer? And last time we talked about race conditions, where two processors were trying to just compute the sum of two numbers, and depending on the order in which loads and additions and stores could occur, you could get a whole bunch of different answers. And so again, we're going to confront that question again when we go on to the next programming model. And so the answer to how to do that was the idea of which operations are atomic. Which ones can you trust that only one processor gets to do them and nobody else is going to interrupt that particular activity? And a line of code in a shared memory program which read s equals s plus 1 was not atomic. It broke down into a sequence of assembly language instructions which, get s from memory, do the addition, put it back. That's at least 3 steps. Those were atomic, but not the whole operation. And we introduced the idea of locks to make sure that only one particular thread could do that line of code, s equals s plus 1 at a time, to prevent getting wrong answers. So that's just sort of a little review. And I also want to say that the reason I have these 2 columns up there is that of programming models on the one side and machine models on the other, is that historically the machine models and programming models have been very tightly coupled. In fact, when people used to build a new architecture, they'd give you a new programming language too, which of course didn't make the programmers very happy. And so now there are standards, so you can be pretty sure that if you write a program today using one of these models, it'll be still work in the future, but it still has to be tied to the architecture. And so the next one that we're going to talk about is message passing programming model. So MPI, this is sort of the main model that scales up to really big machines like Hopper and Edison and the ones you're going to use. And so message passing is the programming model, and the machine models are distributed memory, programming over the whole internet. I sort of gave an allusion to that last time, looking for aliens. And then there's another version of it which tries to combine the last two. So 2A, global address space, tries to combine the best of shared memory and message passing. So it's kind of a hybrid. But so let's go on to 2, which is the message passing programming model. And so again, when you write the program, you can think of it as a collection of processes, so a bunch of sequential programs, one running on each processor, and there's usually a fixed number at startup time. So if you have 64 or 1,000 processors, each one will start executing the same subroutine. But each processor can say, who am I? Am I processor 1, processor 2, processor 3? And then they can branch and do completely different things. But think of one subroutine executing in each processor. So there's no shared data whatsoever. So every variable that you look at in your subroutine in each sequential program running on its own parallel processor only can see its own data. So I, S, all those variables are its own. And so the question is, how do you actually do something useful where there's coordination between the different processors? And so the only way you can coordinate, and so here is the picture here that I have. So each processor here has its own local memory, its own local variables that it can access, and they can communicate over a network. But if I say, please get location 37, it's always mine. It's never anybody else's. So the question is, how do you communicate in this model? And you have to do it by sending messages. You have to call a subroutine which says, please take this piece of information and send it to somebody else. It's like the post office. So you put it in the mail, and you call a subroutine called send my local variable s to processor P1. So you put s in an envelope, put P1 in the front of the envelope, and put it in the mailbox, and the network delivers it. And then processor P1 has to go call another subroutine that matches it called receive, which means please go to my mailbox, open it up, see if something has arrived from processor PN. If it has, open it up, and I take the variable s out, and I can do something with it. And so all of these have to come in pairs, and this is the way communication is done. So it's a lot more, let's say, tedious, perhaps, than the shared memory model, where processor 1 could have just said, go get me S. And the network would have automatically gone over there, but that did not scale. I think I showed you the data to thousands, let alone millions of processors. So this is the way it's going to be done. And so the good news is that this is so popular that there's a committee, again, there's a standard, and everybody's agreed on what's the name of the subroutine, how do you spell send, how do you spell receive. So when you write the code today, it'll be almost surely going to work in a few years. And so because everybody's agreed on this standard, many hundreds of pages, because there's a lot of ways to spell send and receive with slightly different semantics that I'm now going to tell you about. Okay. So let me now say, how would I use the same program that I wanted to show before? I just want to add up two numbers. So processor 1 owns a sub 1, processor 2 owns a sub 2, and I want to compute that sum. And I want both processors to get the value and agree on it. So here is the simplest program you could imagine writing. So let's, just as I did last time, I wrote a simple program and it didn't work. So let's see why this one doesn't work. So processor 1 will compute a local, so these are all local variables. It'll compute f of a1. And then it'll take its local copy there and it'll send it to processor 2. Processor 2 will do the same thing. It'll compute f of a2 and send it to processor 1. Then each processor executes a receive, takes the value from its neighbor and puts it in a local value, and then does the sum. So how could this go wrong? How could this break? And there's a hint there. It depends on whether send and receive acts more like the telephone system or the post office, which have very different semantics. So if they were like the telephone system, here's sort of something you could imagine. You pick up the phone and call processor 2. You pick up the phone, call processor 1. You both get busy signals, and you just sit there waiting forever. You have a deadlock. That's one possible semantics of send. But what if it's like the post office? When you send, you just put it in the mailbox, and then you go on to the next thing that you want to do. You just, you return immediately, and you execute the next subroutine, which is receive. In that case, there's no problem. Everybody will get their neighbor's data, and life will go on. So it turns out that both flavors of send and receive are in this standard library called MPI because they both have their uses. And so you just have to know the difference and call the right one. But let's ask if there's another way to do this, where even if it was like the telephone system, it would work. So here's another way you could imagine trying to do this. So processor 1, again, computes f of a1, sends it to its neighbor, and does a receive. Processor 2 does it in the opposite order. First it does a receive, and then it does a send. And so now, no matter what the semantics are of send and receive, whether they immediately go on or not, these two guys match. So when you call receive, you're going to have to wait. That receive will block. It will say, I'm not going to keep going until this value shows up because I may need it in the next line of code. And so it will wait, but processor 1 has sent it. So these two guys match. The next two lines match. And so couldn't possibly be a deadlock with this possible order. But of course, this is with two processors, and if you have more than two processors, what's the order going to be, right? So that's why there are going to be these different flavors of send and receive, which don't block. So MPI, the message passing interface, is the standard. So over a period of time, every company invented their own ways of doing it, and as usual in this process, they finally said, oh, let's have a standard. And so the good thing about having a standard is that it's portable. So if you write your code today, it's going to work in a few years. People keep adding features. They never take away features. So I'll talk about some of the features they've added recently. I think a new standard came out last year. That's the pro. The con is that it kind of nails you down to some old technology. You sort of have this model of how hardware works, And it may, and if somebody comes up with a new clever idea in the hardware, it may discourage innovation. You know, you may be able to do something more easily in parallel using new ideas, but you know, this is a trade-off. And so here's a quote to illustrate that by Horst Simon, who used to teach this class occasionally, and he's the deputy director at LBL. I'm not sure how I'm going to program, you know, this huge petaflop computer, but I'm sure I'm going to use MPI. And this is sort of a pun on a much older quote, about 30 years older. And that older quote was, I'm not sure what programming language I'm going to program in 30 years, but it'll be called Fortran. So this is meant to be a pun. That one wasn't quite right. And this may or may not be right. I mean, today petaflop computers exist. People program in MPI, but of course, you know, what'll happen in 10 years. So that's the programming model. And now let's talk about the machine model to go with it. What's the hardware look like that makes those sends and receives work? And the canonical machine you'll be using it this semester is the Cray XE6 Hopper, or its successor Edison, or its predecessor Franklin. This has been around for a while. And this was actually done, been around for quite a while. There was kind of a revolution when people realized that you didn't have to buy a supercomputer from Cray. I mean, Cray didn't like this, but you could just go to the local store, buy a bunch of PCs, buy some Ethernet cable, connect them together in your lab, and for a tiny fraction of the price of a Cray, you could build your own parallel computer. And those were called PC clusters. And there was a project where Berkeley was one of the first places to do that. It was called the NOW project. And the one that actually got the most publicity because they made all this public domain software available, you could just download it. And so they built all of this message passing stuff, was called Beowulf. And I'll have another slide on Beowulf. So these machines, you know, that I mentioned, and all these older ones, Millennium used to be a cluster we had in the ECS department. They're all distributed memory machines. Now, of course, if you look inside each node, it's probably it's a multi-core chip. So inside Hopper, for example, you're going to do this P0 here, this single processor, is actually a multi-core chip. So it's a 12-way thing. I'll tell you about that in a second. So here is what all the hardware looks like. So you have a processor. It has a local memory. It's a completely sequential beast. I mean, modulo, it might be multi-core, but from this point of view, let's just think of it as sequential. They're all connected over a network, which is not a bus. It could be like a two-dimensional torus or a three-dimensional torus. People experiment with these things, but it's because it's too expensive to connect everybody to everybody. I mean, if you had 1,000 processors, how many wires would you need to connect everybody to everybody directly, right? And these have 100,000 processors. So the connection is a little bit more complicated, and because of that, they add another piece of hardware called a network interface chip. So there's a special extra processor there that runs in parallel with your processor, which does all the arithmetic, and this has the job of being the post office or the telephone system. So when you call your send routine or your receive routine, all the work is passed on to this network interface card or chip, and it's responsible for doing all the work of, you know, opening the mailboxes and checking the mail and sending things and so forth, and maybe forwarding it because it may take many hops to get from this side of the machine all the way over to that side of the machine. And the processor doesn't get interrupted. It can keep on going, doing useful arithmetic and so forth. So these two, so there's a separate processor to do all the communication. And so let me just say, let's see. Right. So now let me just say a little bit more about the history of how this started. And so this was back in 1994 when people realized they could just go do this by off-the-shelf hardware, very cheap, buy an Ethernet and connect it all together. And so Tom Sterling was the guy who made this very popular and did a great deal of PR. And so the question is, why did he call it Beowulf? It's sort of this ancient poem written, you know, 1,000 years ago. And in that poem, Beowulf is described as having 30 men's heft of grasp in his hand. So he was 30-way parallel back then, 1,000 years ago, in principle, so he decided to use the words there for this, to describe this particular machine. And people continued doing it, you know, ever since. So that's machine model 2A, distributed memory. So I mentioned this one before. This is machine model 2B, which is all the computers in the world connected over the internet. And this has been used, and I mentioned this last time, SETI at home. And when I looked at the data about a year ago, there were 3.3 million computers around the world owned by 1.3 million users who had signed up to look for aliens. And actually, if you look at the web page, which is now called BOINC, the Berkeley Open Infrastructure for Network Computing, you don't just get to look at aliens. There's a list of like 200 different projects. You can fold proteins. You can try to cure malaria. I lost track of all the different things you can sign up to do. But any person can say, I have a project which is embarrassingly parallel. I just need lots of computing cycles. And you can write a little advertisement and put it in this web page. And anybody who thinks it's important to look for aliens or cure malaria can sign up to be sent jobs automatically to your machine if you have spare time and battery power. And it will send you little jobs that hopefully will require a lot of computation, because obviously sending it over the internet is a lot of computation. But then you do local stuff and you send back the answer. And so this has been going on for quite a long time. They haven't found any yet, obviously. We'd have heard about that. So let's see. Oh, the other thing is, if you like mathematics, there's something called the Great Mersenne Prime Search. So looking for the world's largest primes. I think they did find a larger prime than was available before. And if you Google either volunteer computing or BOINC, you will find these things. So, so one of the issues that I mentioned here is, how do you trust people who sign up to do this? And so the way that they deal with that is because people may be motivated to say, I found an alien, because they just want the publicity, or their machine may break. I mean, there's all sorts of things. So they always send out each piece of data, at least the last time that I looked, 3 times. So every piece of data is analyzed 3 times. And it's only if they agree that that the central location would actually say, maybe it's worth looking at. And so that's true. That's sort of a volunteer thing. But when we get to exascale, it's not because you don't trust that processor, but it's because it may break. And so that kind of redundancy is something that's going to come up in the future too. Okay, so that's internet style. And so now I want to talk about one more model which tries to combine the best of both worlds, the fact that people like shared memory. It's kind of pleasant to just write S sub I, and the machine goes and gets S sub I wherever it happens to be stored in this shared memory-like kind of situation, even if it's far away and the machine has to send a message. You don't want to have to type send and receive all the time. And so in that case, what your program looks like is this. You have, again, a collection of subroutines that are called independently in all the different processors. They have threads. And each one can say, am I processor 1 or processor 2, and do branches appropriately. And so here they are, all the n processors. But your memory, when you declare variables, are divided into 2 kinds. Again, there's private. So the I in your loop index, it's private. And then there are other variables which are shared. But and everybody has to agree. So for example, if you have an array S, which is indexed from 0 to n plus 1, everybody has to declare the array S. Everybody has to say it's shared. And then everybody gets one piece of it. So in this case, if it's an array of length n plus 1, everybody gets one number. If it were bigger, it would be divided up into chunks. And so processor 0, when it refers to S sub 0, it's in its local memory. It gets it. It's very fast, no delay. But processor 0 is also allowed to say, refer to S sub 1. And when the compiler sees that you're referring to S sub 1 and realizes that you don't own S sub 1, it will automatically generate a message. It'll communicate with processor 1 to go get the value of S sub 1 for you, so your code doesn't have to look any different. It's going to be a lot slower when you go get S sub 1, but your code won't look any different. So you can write code more quickly, but if you don't pay attention to whether your data is local or not and just refer to everything willy-nilly, it'll go slow, right? So you still have to think about locality. It's just easier to express. And so anyway, so that's an intermediate point. So the question is, how does this map to the hardware? And so it turns out you can run it on the same kind of hardware that people have been using before, because you can program the network interface card to do this job for you of recognizing when you're referring to S1, which has to go over here to processor 1, as opposed to S0, where you can just go grab it because you own it. And so what happens when you refer to suppose you say x equals S1, and I'm processor 0. So what happens is the network interface will recognize that it needs to go S1. That network interface will talk to processor's 1 network's interface, and it'll grab it directly out of the memory. It will not interrupt processor 1. So processor 1 doesn't have to pay any attention, completely asynchronously. My network interface will talk to that network interface to get the value, and it'll just get grabbed. So that makes it easier to write the code. And similarly, if I'm processor 0 and I say S sub 1 equals 7, then what my network interface do, it'll send a message over to this network interface, and that guy will talk to the memory and change the value of S sub 1 to 7. just on the fly, without telling processor when it happened. So you can imagine there are going to be some race conditions, and you have to worry about it. I mean, so that you can't get away from having locks and so forth, but it's just much easier to do that, to express code that way. And there are a lot of ways it can go wrong, but it works quite well for people who happen to like it that way. Okay, so somebody in the last lecture, when I gave this a while ago, asked the following question, so let me just anticipate it, which is, why not implement this the same way people tried to implement this model, which was distributed shared memory. You may remember they had these big tables locally, which sort of kept track of which variables were local and which ones were remote. And the answer is that couldn't scale past 512 processors, because the amount of hardware you needed to keep track of all that just kept growing and growing. This runs on the biggest machines in the world. So because when I go and get the value S1, when processor 0 says, please get S1 from over here, it doesn't go in the cache. It's not cached. And so there's no need to do cache coherence. So that's how it works. That way it can scale up. Okay. So we just finished now shared memory, message passing in this global address space stuff. And the next model, if there are no questions, is going to be the data parallel kind of thing. So GPUs being a canonical example today of the biggest kind. So here's what the programming model looks like for data parallel. And maybe MATLAB is one of the easiest examples to think of. So imagine you write one line of code, A equals B plus C, and B and C are arrays of length n. A is an array of length n. It just means add each entry, do it all in parallel. And that's certainly an easy way to express code. And so, of course, we don't want to just have operations like this. We'd like to be able to say, take the first 10 entries of this array, add them to the last 10 entries of that array, and put them somewhere in the middle of that array. So you need to have nice machinery to let you refer to subarrays. And if you're used to programming in MATLAB, that's not unusual. B sub 0 colon 10 or something like that. So it's nice and easy to express. Arrays are the most common data structures that you program in. The parallelism is implicit. That plus sign and that equal sign automatically say do it in parallel if the data structures happen to be big enough to do that. The coordination is explicit. Your code looks perfectly sequential. If this line of code, when you execute it, it has to finish before you go on to the next line of code, which may be B equals A plus C or something. So this one finishes, it's done, there's a barrier, so to speak, and then it goes on to the next line of code. So, of course, even though people like to program this way, it's hard to write every parallel program using these kinds of expressions, but it has, when you can, it's nice. So the problem we've talked about so far, which is adding up a bunch of numbers, is really just 2 or 3 lines of code. I would initialize my array A, and to have all the data. This would be spread out over all the machines automatically. Then I would compute f of each value. So this is a new array, and when I compute f of an array, it just means value by value, embarrassingly parallel. And then almost all of these, all of these data parallel languages have built-in functions which take a whole array and they reduce it by a sum or a product or a min or a max, something like that, into a single scalar, which then everybody shares. And so this is actually where the name MapReduce comes from. Which is the cloud computing kind of framework. Because what is a map? It's simply f of a. Take some array of data that's spread out across the machine, like all these web pages, and compute some function of it, which is the list of the keywords in it or something like that. And then the sum is a reduction where you just reduce it all, and the answer pops out, which is either the sum or the favorite web page that you want to report to the user. So this is how lots of things get built at companies like Google. So that is the programming model that comes up in lots of places. And what does the hardware look like when people have in the past built special purpose hardware for this? So in this case, the easiest way to think about it is there's one control processor. There's one processor that actually executes the list of instructions. But now a single instruction can say, please take these 1,000 numbers and add them to those 1,000 numbers. And when that instruction is executed, the control processor sends out that instruction to a whole array of little processors, which are slaves. They're only allowed to do what the control processor tells them to do. And so each of these will do one addition or one multiplier, maybe something more complicated. And that's where the parallelism comes from. So why is this called SIMD? That's an old abbreviation. It's called single instruction, multiple data. So that means the control processor executes a single instruction, but it applies it to multiple data. And this is a natural paradigm, been around for a long time. And you also have options. For example, if you only want to do it on the odd-numbered subsets of an array, the control processor could just have the odd-numbered processors turn themselves on, and the even ones would turn themselves off. So there's all sorts of other options too. So going back historically, there were a lot of special purpose machines that were built this way. The connection machine 2, the MassPar, old Cray vector machines, and they sort of went away. They've all kind of died out, but it's come back because that's what SSE2 instructions are. That's what the AVX instructions are in just about every small processor, because people have realized, well, there's a lot of use for it. Maybe not at the 1,000-fold level. That's what GPUs are for, but certainly at the 2 or the 4 or the 8, that's in pretty much every processor now. Okay. So those are SIMD. And I guess I do want to mention these vector processors that I had mentioned before, where there are these multiple functional units all performing the same operation. And those were, as I said, when people realized you could just go to the store and buy a bunch of commercial off-the-shelf microprocessors, connect them over an Ethernet, they became less interesting. But they have reemerged. And so I showed you a plot of the top 500 where there was this machine that was in the top for five races in a row. That was the Earth simulator. And that turned out to be a vector machine that they built. And as I mentioned, it's in all of these different kind of commonly used processors. And it's at a much larger scale in GPUs. So let me just sort of talk about one more lower level thing about how these things are implemented. And so, so here, you can imagine I have this register, I have that register, and I want to do an addition, and it comes out in that register. So what a vector processor did, they actually had, when you refer to a register, that register could actually store 32 or 64 numbers in it. So, and they were quite longer back before SSE2 and so forth. And so the addition instruction was applied to each pair of inputs to get you the output. And so the way that was built typically was by pipelining. So for example, suppose you could do 2 processors at the same time, then it would go in a sequence and it would take the first 2 pairs of arguments, compute their sum in parallel, then it would do the next 2, and then it would do the next 2, and it would pipeline it all the way through. And so this is just the way these things were built. So let me show you the Earth simulator. And the reason this is historically interesting, besides the fact that it was the fastest machine in the world for sort of 5 races in a row, it was very large. It filled a tennis court. And the Japanese government invested an enormous amount of money to have not a complete connection to everybody, but they had more wires and a special building to hold them all than anybody had ever connected before. And so it was interesting because I was sitting on an NRC committee, and we were writing a report on the future of supercomputing, and so we were looking at all these things. And we decided to ask ourselves the question, well, what is the speed of light across a tennis court? If you follow all these wires that they'd actually built, and ask exactly how many hundreds of meters long they are, how long does it actually take to send a message from one side of this machine to another? And it turned out it was 1/10 of a microsecond. So there was a lot of distance there. And then we asked, well, if you call the MPI subroutine to do a send or a receive, how long does it take? And it was 10 microseconds. So they were within a factor of 100 of the speed of light. So it was clear that there's a factor of 100 is pretty big, but they were getting close, right, to a real physical limit that clever hardware is never going to beat. So they gave up looking for those neutrinos that supposedly went faster than the speed of light. We're going to live with this for quite a while. And so that's what set off a lot of research to try to minimize communication, because people are getting close to these lower bounds. Okay, so so that ends what I wanted to say about data parallel. And so, but the last bullet is to say that the real machines that people program are actually hybrids of all of these. They're heterogeneous collections of all these different things. And so, in fact, the biggest machines in the world that make up the top 500 are very complicated collections of all these different technologies, which makes programming them, if you really want to go fast, quite a challenge. So, in particular, the things that are in your laptop, those multi-core chips, are the building blocks that are inside these fastest machines. Even if you have a cluster, if you look at each processor, it's a multi-core chip. And people invented this old name for them, clusters of SMPs, of shared memory processors. They called them clumps, but people have come up with names like this for a long time. So for example, Edison and Hopper Those, if you say, what's one node that's running MPI, it's actually 2 multi-core chips, and each multi-core chip has 12 cores on it. So there's 24-way parallelism inside each node on Hopper or Edison. Hopper is AMD chips and Edison is Intel chips, but it's still 24-way parallelism inside each node. And this is true, in fact, on most of the top 500. So the question is, how do you program a machine like this that has all these combinations? And so the easiest way to do it is just to ignore the fact that there's these layers, this hierarchy, and treat the machine as flat. So just call MPI. So every core runs a separate MPI process. And even though it's shared memory, you still do sends and receives with the processor with whom you have shared memory. And that's simple, but it sort of adds a lot of overhead to the runtime because of all of this stuff going on. So people are trying to build versions of MPI that are smart enough to know, oh, you don't have to send a message. It really is shared memory, but it doesn't always work yet. The other way that people who absolutely want to go as fast as possible do is that they just bite the bullet and they write 2 levels of code. They write MPI code that sends messages, 1 MPI program per node, let's say per 24 cores, and then inside those 24 cores, those 2 multi-core chips, they will write pthreads code or OpenMP or shared memory code is what they will write. And so that makes code rather difficult to maintain and so forth from one generation to another, but if you want the peak speed, this is what people have done. So to make it even more interesting, the fastest machines in the world not only have a whole bunch of different nodes. Inside the node you have multi-core, they have GPUs attached. And so in addition to deciding what to use MPI or OpenMP, you have to decide what subset of your work you're going to ship off to the GPU that you're attached to and ask it to do. And so if you look at the top 500, only 10%, there are 10% of those machines, so about 50 of them, have accelerators, so some flavor of GPU attached to each node. But in fact, if you just look at those 10% of those machines, that's 35% of all the performance. So the fastest machines in the world are indeed these really difficult to program heterogeneous clusters. And that's just the way the world is. So as I mentioned, you can have message passing at the top with shared memory within a node. DARPA funded a program a few years ago to try to come up with some new languages to mix data parallelism and global address space languages. It's not clear that they're taking off so much, but people are trying to realize these things are hard to program. You can have global address space, so you can write code that I mentioned, UPC, where you can refer to S1, and it'll automatically recognize it's remote. But people mix those by calling, let's say, a library which does MPI on the inside. So you have to be able to mix these different programming models. And so anyway, this is what the world is really like. We're not going to, you're welcome to do this in your final project. To go into this depth, you can also choose to say, I want to program at a higher level and hope that everything is hidden for me. Okay, so I've mentioned a little bit about GPUs and cloud computing. So let me just have one more, and we're going to have guest lectures on both of them in a little bit more detail, because their programming models are quite different. Because they've invented special languages for both of them. So I just want to mention that. This is more of an advertisement for later lectures. So GPUs, it's all data parallel. You can have single instructions that can do not just, if you read the manual, it says the best way to organize your code is to do 10,000 things at the same time. Have one instruction that does that. So why were GPUs invented? By the way, GPU stands for Graphics Processing Unit. They were meant to draw pictures on your screen. And so if you can imagine each pixel on your screen, you're running a separate process. There are a lot of pixels, and they were designed to specifically do that kind of real-time picture generation. And then they realized there was also a market in high-performance computing, and so they added a bunch of features to make it easier to do scientific computing. But still, the best way to make them busy is to do really thousands of things at the same time. NVIDIA, which is one of the platforms in which you'll be doing a homework assignment, has its own programming language called CUDA, so it's a flavor of C that lets you express this very massive parallelism. And in the meantime, a lot of other companies are trying to produce similar kinds of architectures, and as usual, there's a committee that's been formed to try to come up with a common language so that you can write the program once and have it run on NVIDIA hardware and Intel hardware and AMD hardware. And the language design they have right now is called OpenCL, and it's still very new and under development. And we'll have a guest lecture later in the semester, actually by a former graduate student here in the Par Lab who now is a staff person at NVIDIA, so he will come and talk about that, Brian Catanzaro. So cloud computing, where did that come from? Well, companies like Google and Amazon built these huge warehouses full of computers to do their web search and so forth. And then they realized there was a market for letting other people use them, right? So you can just go to a web page and put in your credit card number and program, 100,000 computers, and it'll charge you appropriately, depending on how many you use. And so, and what are the programming models that they make available? Well, the first one that I mentioned was MapReduce, where you do something embarrassingly parallel and then you reduce it all to find the most popular web page. But there's been a lot of innovation to try to make more flexible programming models. In fact, in the AMP lab here, they've produced several such extensions, more flexible models that have turned into startups. They've been adopted by various big companies in Silicon Valley, and we'll have another guest lecture on that later in the semester by one of the main people in the lab who's been working on these things. And these are all fair game for class projects. Okay, so that's most of the end of this lecture. So let me just tell you what the lessons are. So there's three basic conceptual models of how hardware can look. There's shared memory, there's distributed memory, and there's data parallel, and there's lots of different hybrids of these. And they all have to answer three questions, which is how do you control parallelism? How do you express that there are many things that can be done at the same time? How do you express data? What's private? What's shared? How do you communicate it? And then synchronization. How do you get these multiple processes to agree when to stop, when to share? So now to make code run fast, you have to solve the same set of problems. You have to divide up your work into parts, tasks that are mostly independent, so they don't have to synchronize with one another very often, that they're about the same size, so that they're load balanced, and so that they have most of their data can be stored locally, so they don't have to communicate very much. Now, it turns out that figuring out how to do that division is been thought about a lot, and there are certain patterns that come up over and over again. And so the next lecture is going to be how do I identify these three opportunities in a very large class of problems, which is basically simulations of different kinds. So, so how do you automatically recognize opportunities for parallelism and locality in applications? And so the next 1.5 lectures are going to be, now we're going to go to the top of the stack, look at applications, and say, how do these things come up all the time? And how do you recognize them? And so if there are no questions, I'm going to switch PowerPoint, and Aditya is going to tell you about some logistics.
So hey folks, just
so let's just see if are there any questions before Aditya talks about. Okay, yes, microphone.
Is it correct that GPUs are all single precision floating point arithmetic?
That originally they were designed to have single precision, which is to say 32-bit, about 8 decimal place arithmetic. And that was good enough for graphics, because it didn't really matter exactly how Darth Vader smashed something to how many decimal places. But now that there's a market for scientific computing, they've added double precision.
Oh, cool.
And the original versions of it went at least 4 times slower. And so there was still a hit. But now I think in some of the more recent processors, the gap in performance between single and double has been closing. So.
Okay, so a couple of announcements. First, homework 0 is due tomorrow at midnight, so hopefully you guys are making progress on that. The other thing is there was one person that had a question, and I'm sure some of you saw it on Piazza, about office hours. So Razvan and I have joint office hours on Friday from 2 to 3. So the question was whether we could hold separate office hours so that you guys have different times to choose from. So just a show of hands, how many of you guys would like joint office hours? Okay, so how about separate times? Perfect. So this makes it much easier. I'll probably throw on a poll on Piazza just to make sure that you guys have a say in what times work. So stay tuned for that. So you can also find the office hours on the course webpage. So.
Have I put the most recent office hours on the course
yes.
webpage?
So let me just recap what the office hours are. So Monday, Wednesday, and Friday from 10 to 11 are Jim's office hours. And those might change depending on meetings and things like that. So Razvan has office hours on Monday and Friday from 2 to 3. And I have office hours on Wednesday and Friday, 2 to 3. And of course, one of those times will change so that you guys have a better spread.
Okay. So the next topic for the next 1.5 lectures is going to be how do you easily recognize that there are a lot of sources of parallelism and locality in simulation. So I'm going to tell you what I mean by simulation. It's going to have a very wide range of things from very discrete to very continuous. You'll see. So parallelism and locality are both critical to performance, and I think I've made that point that moving data is the most expensive operation. And so the good thing is that many real-world problems that we want to simulate automatically have parallelism and locality. If you just think about the physics or the sociology or the chemistry of whatever it is that makes it work. And so I'm standing up here talking, and you're off all sitting in the audience doing whatever you're doing. So you're a completely independent process than I am. And if I'm a particle bouncing around and you're a particle over there bouncing around, you're moving under F equals ma, I'm moving under F equals ma. That's clearly independent until we get close together. And in fact, that's the next point. Objects often depend much more on nearby objects than on distant objects. And so the simplest example is billiard balls, which is going to be one of your assignments. Until two billiard balls get so close together that they collide, they have nothing to do with one another. They're completely independently rolling around. But even for gravity, you depend much more on your nearby particles than you do on particles that are farther away. Electrostatics too. So imagine I wanted to compute the force of gravity on the Earth in some big simulation. I certainly have to know where the moon is. I have to know where the sun is. But when I go out up at night and look up in the sky and I see lots and lots of little white dots, one of those dots is the Andromeda Galaxy. And I say, oops, there's another billion white dots inside the Andromeda Galaxy. But no, it's perfectly fine to approximate the Andromeda Galaxy by a single point mass at its center of gravity, and that's good to as many decimal places as you'll ever want. And from Andromeda's point of view, the Milky Way is a point mass. And so in fact, we'll use that later, not today, but in a later lecture to get the complexity where everybody has to talk to everybody, it sounds like, right? In gravity, everybody depends on everybody else. It sounds like you have to do n squared work to do it. By taking advantage of that opportunity that the Andromeda looks like a point, Milky Way looks like a point, you can get the complexity down from n squared to n, which is optimal. And so, and that's a very famous algorithm that we'll talk about. So that's another fact. And so, in fact, that's my third bullet. The dependence on distant objects can be simplified, as I said. So you can get the complexity of gravity down from n squared to order n. So then, when you actually take a model of the real world and you come up with some discrete version of it, so you have a differential equation, you can't solve that continuous problem, you have to evaluate it at a bunch of discrete points on a grid, that introduces yet more parallelism. So, and that's because, let's say you're trying to solve you do time stepping, you're trying to solve some differential equation or dynamical system that evolves over time. It turns out that when you write down the discretization, your value at the next time step only depends on your nearest neighbors, because information doesn't travel, if you've written down the equation correctly, farther than your nearest neighbors. And so that limits how much communication you can possibly have when you've done the discretization correctly. And so, all of these things come up over and over again, and so I'm just going to show you lots of examples at a high level to make sure that you recognize them when it's there. And of course, many problems exhibit this kind of parallelism at multiple levels, and so I'm going to show you several examples. And so let me walk through the basic kinds of simulations that we're going to talk about. And the first one is called discrete event systems. In that case, everything that in the system that you're trying to simulate is discrete. The time is discrete, time steps, the objects are discrete, and the rules or events which say when you change from one stage to another, they're all kind of discrete. And the classical example, if you remember Scientific American from a long time ago, is the game of life. So you have a two-dimensional grid. Each grid point is either dead or alive. And to go from one time step to the next, you look at your 8 nearest neighbors and your own value, and there's some simple rule. You take those 9 values of dead and alive, and you decide if you're dead or alive in the next time step. So that's also called a finite state machine. Another example would be a manufacturing system. You have an assembly line. Things, there's sort of discrete events that occur there. Raw materials are supplied. They're added in, and something pops out at the end at a certain rate. You want to analyze that. That's another kind of discrete event system. Finance, those are financial transactions that occur at fixed time periods. Those are certainly discrete, although I'm going to use finance later as an example that you can also do continuously. And circuits you can do at any level, but if you think about a digital circuit where everything is a 0 or a 1, and in every time step you take some values, some trues and falses, and you do ors or ands, you get the next value at the next time step. That's a canonical discrete event system, and many people have written simulators used in industry that do that. And then I'm going to use computer games also. So Pac-Man, if you remember that guy, is an example of a discrete event simulation. So the next level, I'm going to have these 4 different flavors. That's discrete event, everything is discrete. The next one is going to be a little bit more continuous. So particle systems. So in this case, what is discrete? I have a discrete set of particles, billiard balls, atoms, whatever, but they're going to evolve continuously in time. I'm only going to evaluate them at certain time steps, but what's discrete is where all the particles are. And so again, billiard balls, they're going to move in straight lines under F equals ma until they collide. So there's going to be a separate rule for how they collide. Galaxies moving under gravity, I mentioned that one already. Molecular dynamics, in that case you have electrostatic and other forces, but each particle is sort of moving around subject to that. Now for circuits, that's another example that people sometimes simulate at. You have electrons and you ask where are the electrons, and they move around, and you can simulate at that level too. And finally you get to another level of game, which is pinball, which some of you may have played as well. So let me make things a little bit more continuous. And these are called lumped variables depending on continuous parameters. And so particle systems are a special case of this. And another name for these things are, well, you might think these are just ordinary differential equations, but it's actually a little bit more complicated than that, because you can also have constraints. And like Kirchhoff's laws if you're an electrical engineer. So you can have things that change, but they have to change subject to certain kinds of constraints. So here a classical example is structural mechanics. You want to know if this building is going to fall down. So you write down the position of every girder and beam in the building. Everybody's connected to their nearest neighbors. And there are certain rules of elasticity and force and so forth. And you ask, how does the building move over time as I shake the bottom of it? So that's a differential equation. Chemical kinetics, the same idea. You write down, in that case, the variables that change over time, of which there's a discrete set, are the concentrations of a bunch of chemicals that depend on the other chemicals in there. So what is still discrete is that I have a finite number of objects that I'm tracking, a finite number of chemicals, a finite number of places in the building that I track their position. But what's continuous now is time. Circuit simulation is another example. So there's a very famous circuit simulator called SPICE, which was invented here at Berkeley and is widely used in Silicon Valley. So in that case, you write down equations for the voltage at each point in the circuit and the current, and you write down lots of classical equations from electrical engineering, and it tells you what's going to happen. And then, just to go up one more level in the game world, there's Star Wars: The Force Unleashed. So that is a computer game that does real-time finite element simulation in parallel, so that when Darth Vader smashes something, it's getting the physics right, so it looks good. And so this is because it's possible to get the physics right on these GPUs and give you that game experience. So the last one is everything is continuous. And continuous variables depending on continuous parameters. And another word for this is partial differential equations. And so, for example, you may have the heat equation. In that case, the temperature is the answer you want, and it depends continuously on where you are in space, and it depends continuously on time. And when you try to solve it, of course, you put down a grid. You're only going to measure the temperature at a fixed number of grid points in time and a fixed number of grid points in space. But that's one example. So elasticity is another one for the building. So in that case, it's sort of force and bending and so forth at every point. Electrostatics, that's sort of the Poisson equation, or various versions of it that says how things move and what the electrostatic force is. So I have finance at both ends here, and it turns out that if you're trying to model the prices of derivatives, you can write down what's called a stochastic differential equation, because it's kind of random how finance works. And if you do that at the right time, you win a Nobel Prize in economics. Those are the Black-Scholes equations from 1997 when they won the Nobel Prize. So for circuits, you can also, if you write down Schrödinger's equation for where all the electrons are in a piece of silicon, you could model a circuit at that level. And you probably don't model a very big circuit, but you might model an individual transistor that way. Medical image analysis. And then there's Terminator 3. And so Rise of the Machines. And so what they did there was that every time so there's all this fluid splashing around, not just water. And so, whenever our ex-governor, splashed something, they would get the physics right and make sure it looked very good. So this is the most continuous version of all. And the other difference that's worth pointing out between Star Wars: The Force Unleashed and Terminator 3 is that most of the development of the underlying technology for Star Wars: The Force Unleashed was done at Berkeley, and Terminator 3 was done at Stanford. But otherwise, they're both very interesting, and I'll show you some fun pictures later. And so if you can't wait till I show you the video of Star Wars: The Force Unleashed, you can just go to that website and click on it. But I'll show it to you in the next lecture. So just to show you that simulation occurs at many different levels, let me just pick one kind of simulation, which is circuits, since there are a lot of EE students here. I hope you appreciate it. And you can simulate it at every level, from everything being discrete all the way down to continuous. And all of these have commercial tools that are widely used in order to do these levels of simulation. So at the most discrete level, that would be sort of instruction by instruction. You have, this instruction says, add these two registers, put the answer over there. So in that case, the primitive level is an instruction, and you just go clock cycle by clock cycle. And these are two packages that do that for you. So that's the most discrete. I can sort of go at a next level of resolution and say that, well, what happens inside an instruction? It actually takes several cycles to execute an instruction. And the instruction isn't just add, it's built out of various functional units. There might be an adder and a multiplier and various other things that move things around. So I could do it at that level and have one step at a time, cycle by cycle. If you look one level down below that and say where are all the registers where things actually live, that's called register transfer level, or RTL. And that is a language in which electrical engineers write low-level circuits. In that case, the primitives are the counters and the muxes and the registers. And there's more tools at that level. You could go all the way down to a gate, so a single 0 or a 1, and those are the flip-flops and memory cells. And there's more level switches there. You could do it transistor by transistor. So those are all discrete. Finally, you could say, I really want to write down Kirchhoff's laws and Ohm's law and all those different laws, and write down a set of differential equations with the resistors and capacitors. That's the SPICE simulator. And finally, you could write down Schrödinger's equation where all the electrons are in a little piece of silicon, and that's the most continuous way. And so all the commercial tools are generally that you can buy and download are up there. So to outline what the rest of the lecture today and next time is going to be like, here are the 4 different examples. I'm going to talk about discrete event systems. Time and space are discrete, and give you examples of how do you automatically find parallelism, what are the problems that come up over and over again that you've got to solve. Then I'll do particle systems. Then I'll do lumped system with ODEs. So there, the locations and the entities that you're modeling, like the voltage at this particular point in the circuit, they're all discrete, but now time is continuous. And then everything is being continuous. Okay. So I'm going to give you lots of examples, but there's one thing that's useful to look at is sort of one simple model problem. I mean, if I don't want to have to explain the physics, of all of these different examples. I don't know all the physics myself. I want to have some, because you don't need to know that to know how to parallelize it, right? The patterns are kind of independent of the physics. And so what we've done is we've built a bunch of, simplified examples of sharks and fish swimming around under some completely made-up rules that do illustrate all these different kinds of parallelism. And they're all posted on the web page, so if you want to see examples of how people have parallelized these things before. And so the basic idea is you have a bunch of sharks and fish living in an ocean, and there are rules for how they swim around. There's both continuous versions where they actually swim around continuously, and discrete versions where they just live on a grid. And there's rules for breeding, how do fish have babies, and whether they eat. You can imagine sharks eat fish, and then the fish go away, or they may be crowded out and die that way. And they're not just choosing to swim where they want. There's forces in the ocean currents, so that's pushing them all around. And then you can imagine that the sharks are attracted to the fish, and the fish are not attracted to the sharks, so there's these interparticle forces. And it's all kind of made up, but if you can parallelize this, you can parallelize everything else too. And so we have a whole bunch of different versions there that have been programmed in all these different programming languages. So you can see how, if you look at the MATLAB code, you can see the physics expressed, the pseudo-physics expressed in a very simple way. But we've also done it in all these others, including some languages that have kind of died by now, because we've been building this web page for a long time. But these are still useful, and so you could use these as models if you have questions about how to get started in the homework. So here are the 6 flavors of sharks and fish for which we have simulations on the web page. The simplest one is that they're only fish, no sharks, and they're all swimming around continuously, and they don't pay attention to one another at all. They just depend on the external current, so the water's flowing in different places of the ocean in Newton's laws. So just basically F equals ma all independently. So the next thing we add is the fish attract one another. They like to form schools, so there's some gravity in there, simple rules of gravity, but there's also the current pushing them around, so you can see how they sort of swirl around and collect. Those are both continuous. The next version is the game of life, so it's again just fish, and they live in independent grid cells, and depending on your nearest neighbors on this 2x2 mesh, you'll either stay alive, the fish will either stay alive, it'll be born if it was empty, if it has the right number of neighbors, or it could starve and die. So that's an easy one. The next one is a little bit harder because there's all sorts of synchronization you have to do. The fish can't die, they're moving on a grid, so if you have this fish here and this fish here, and this fish wants to move there, they can't sit on top of one another. And so you have a lot more synchronization to do to try to come up with a consistent set so that you don't have 2 fish sitting on top of one another. Then we have the sharks, and so there's at most 1 fish or shark per grid point, and there's rules like the game of life for eating and breeding and dying and so forth. And then finally we make it all continuous, which is the hardest one. Okay. So we're not going to assign these things, but you can just sort of look at them for models of how things might get parallelized. So now we're going to go back to everything being discrete and talk about how to parallelize that. So how are these things represented? You have a finite set of variables because I have a discrete set. The set of all the values at any given time is called the state. So if you have a computer with a finite amount of memory, the variables are each value in the memory, and the state is the value stored there. That would be the simplest example. And so the question is, what does this thing do? There's a function called the transition function, which says at every time step, what is the new value of this particular variable? I look at a certain subset of all the values, and I compute that function. That's my new value. So in the game of life, you look at your nearest neighbors, and you just compute some function and decide what's my new value. So there are 2 kinds of discrete event systems people simulate. I'll call them synchronous and asynchronous. And synchronous is sort of the easiest one. There's a clock. There's a time step. And at every time step, you look at your neighbor's values at the previous time step and update your new one. And so things march ahead in time, and that's a perfectly natural way to do things. That's how computers work. But there are a lot of systems that don't work that way very well, and I'm going to call them asynchronous. And in that case, the transition function is only evaluated if the inputs change. So that means that if your inputs don't change for a long time, if there's no event causing you to change, you don't want to waste time checking the input all the time. So this is called event-driven simulation. And there's a whole bunch of different examples of that I'll use. So I think you can imagine sort of real-life events. You're not going to take an action unless some event causes you to do so. So you don't want to check every microsecond, has something occurred, right? So that's going to be asynchronous. And so let me give you an example now, very specifically. And I'm going to simulate it in 2 ways, both synchronously and asynchronously, but let me define it. It's the game of life, and it's also called sharks and fish number 3. And so the space is divided into cells, and there are going to be some rules that govern the cell contents at each step. So let me write it down and explain how we're going to parallelize it. We're going to do the synchronous one first. And so I have this 2-dimensional grid that has the values of the state at each point, but I'm going to need 2 copies of it, the old and the new. So at every time step, what I'm going to do is I'm going to get the old values, let's say at time t equals 0 of all the grid points, and I'm going to compute my transition function and figure out what the new state values are, and I'm going to copy that in the new array and leave the old one alone, right? If I overwrote this, then I could get into funny race conditions and get the wrong answer, right? So I have an old data, and I copy into the new data. That's the first time step. And the second time step, they swap their roles. The new becomes the old value, and the old becomes the new. So I compute these as inputs, and I update that guy. And so I ping pong back and forth, so I need exactly 2 copies to have a consistent simulation going forward. And there's a time step, right? So I do this once every time step. So the question is, how am I going to parallelize this? And in this very simple example, I think your intuition let me appeal to it. I'm just going to think of them as all living in this two-dimensional mesh, so suppose it's a square, and that's a physical domain, so I'm going to decompose the domain. And so imagine I have 9 processors, and what I need to do is assign some subset of the points, so there's a whole bunch of different points in each of these on this grid, and processor 1 owns that square subset, processor 2 owns that square subset, and so forth. And so everybody owns 1/9 of the data, so that makes it perfectly load balanced. And so what is the simulation algorithm going to be? I'm going to repeat until I'm done simulating. I'm going to take all of the points interior to what I own, where all of my nearest neighbors are mine, and that I don't have to talk to anybody. I can update them, so everybody who's not too close to the border can be updated independently of everybody else. And then I do a barrier. I wait until everybody says they're done. So this is sort of a synchronization subroutine. So all the processors are going to be done at the same time. Now, if I want to update the values that are just on my border there, where one of the neighbors is owned by the other processor, processor 6, I now need to communicate. But since I'm at this barrier point, I know that processor 6 has all those values ready to send me. I have all these values ready to send to processor 6, so I exchange them. And so I take all the values along the border and I exchange them with my neighbors on all 8 sides. And so that's the exchange state information with neighbors. And now I have, and that's not very much because it's just along the border, and now I can finish updating all the stuff along the border. And I just kind of repeat doing that. So I clearly have good locality by doing this. I only need to have the values on the boundary. Most of the work is happening on the inside, and that's local. I own it. And so this is good. And the general question I want to ask is, here it seemed intuitive that I want to pick squares, but there's a lot of different shapes. And if this whole region were not square, then I'd have really a much more complicated problem. So the question is, how do I pick the shapes of these domains? And maybe there's a microphone?
I think it's short enough for you to restate it.
Okay, I'll restate.
Implicitly, the grid size is fixed. Like Game of Life, you can grow the grid size.
So the question was, here I have fixed the problem size to be, let's say, an n by n mesh. But in the game of life, the particles can march off to infinity, and yes, and I will talk about that later, how one deals with that particular problem. Okay, so let me talk about how to divide it up in this case where I have a fixed n by n mesh. And to make it a little bit easier, let's suppose I'm not talking to 8 neighbors, I'm just talking to my 4 neighbors, the north, south, east, and west neighbors. And I want to imagine 2 different partitions, just to show you. I mean, there's a large number of different partitions. So suppose I have an 18 by 18 mesh, and I want to split it up among 9 processors. So here's my 18 by 18 mesh, and each point is going to depend on its 4 neighbors, and the question is, how should I divide it up into 9 different equal-sized pieces? So one simple way to do it is to assign 2 rows to each processor, and I've color-coded the assignment here. So the red processor owns the first 2 rows, and the blue processor owns the next 2. And so clearly this is load balanced. Everybody has exactly 1/9 of the work. And the other way was the one I showed you on the previous slide, where I divided up into squares. So now the red processor owns that square subset, and the blue processor owns that subset. And so the question is, how do I decide which one of these is better? And so they both have the same amount of work to do in computation, but they're going to communicate different amounts. So let me talk about how to count that amount of work. And so how much does this guy have to communicate? How much do the red and blue processors have to communicate? Well, each edge in this mesh that goes from red to blue represents a word of information that has to move. So all I have to do is count the number of edges that connect 2 different colors. And this is a pretty simple thing to do. And for this guy, if you do the counting, ask how many edge crossings are there from one color to another, there's n times p minus 1 crossings that go, if I have a general n by n mesh and p minus 1. If you do the same counting over here, it's easy to count how many edges there are, and it's a factor of the square root of p smaller. And so if p is large, which is the interesting case, this is a significant win over that. And so, and that was our intuition that I used in the last slide anyway, that these squares go. But I want to generalize this to something way beyond squares, because not everything is quite this easy. And so in general, if I want to minimize the communication here, how did I choose this over that? I basically minimize the surface to volume ratio of this partition, or the perimeter to area, if you like. So the volume is the number of points on the inside. That's the amount of work that I'm fixed given, that one piece of all the work. And the surface area, the perimeter, that's proportional to the communication. And so what I want to do is figure out how to choose that to minimize it, surface volume ratio. And in the case of a nice simple graph like this, we can sort of do it by eyeball. But if I gave you something with arbitrary interconnections, that's going to be much harder. So in fact, simple geometry, what is the geometric shape that minimizes the surface to volume ratio just in a two-dimensional planar mesh? A circle, right? So I can't really tile the plane using circles very well, right? So I need to have something else that I do. So let me now generalize this to kind of arbitrary interconnections, which is what I have to do. And so I'm going to use the language of graph theory. So graphs are something which come up all the time. And so just to remind you, what is a graph? It's a bunch of vertices, points, connected by edges. And I can use that to represent any kind of connectivity that I want. And if I'm trying to simulate a circuit, then the graph in particular is the individual pieces in the circuit, the capacitors and the resistors and whatever. And the edges are the wires. Those are who is connected to whom. And so I need to assign different vertices of the graph to different processors. And the edges are going to represent the communication that has to move between these two vertices in order to update the simulation. So what I'm going to do is talk about the synchronous case. So at every time step, each of these guys has a certain state, their value. And what they need to do is talk to all the neighbors to whom they're connected by an edge, get some information, and then update their value. And the question is, how do I do this assignment so that I have to communicate to different processors as infrequently as possible? This is a famous problem in computer science. It's called the graph partitioning problem. And so what I have is a graph with a certain given number of vertices and edges, and I want to break it up into, say, 4 pieces. And what is the constraint? I want to assign an equal number of vertices to each piece. That's the load balancing problem. And I want to minimize the number of edges that go from one piece to another. That's what's going to minimize communication. So here are 2 examples. Let me just do it. So here I have a very simple graph where I'm just connected in this simple pattern. And I want to divide it over 4 processors. And here are 2 intuitive ways to do it. I could divide it up this way or that way. There are many more. So which one is better? So what I'm going to do is I'm going to count how many edges cross from one colored processor to another. And here it's 2 plus 2 plus 2 or 6. And here everybody crosses. And so it's 10. And so this guy is the winner. And in general, for meshes, I could see that, okay, squares, whatever, that's a pretty good idea. But if you ask it for an arbitrary graph, and in general we will have quite general graphs, it turns into a famous computer science problem. It's called NP-hard. So how many people have heard NP-hard before? Okay, so just to summarize briefly, this problem, to get the perfect answer, to minimize the number of edge crossings, nobody knows an algorithm that's faster than exponential. So 2 to the power the number of edges and vertices. So if we could solve, that's probably so much more expensive than the problem we want to solve in the first place. We're not going to do it. So instead, what we're going to do is come up with a decent approximation. We're perfectly happy not to get the minimum number of edge crossings, just make it small, right? That's all we need to be satisfied with the running time. And this is such a common problem that people have built wonderful libraries. There's lots of software that exists now to give us good approximations to this problem. So whenever you see this, you should not say, oh, I have to solve an NP-hard problem. The question is, which library should I use? So, and we'll have a lecture later in the semester on, there are a lot of different libraries because there is no one best algorithm for doing this. It kind of depends on the structure of your graph. Okay, so that's synchronous simulation. There's a graph partitioning problem. So now let's talk about what happens if, and this is more of your question, I have a rather irregular domain, which can be rather empty parts of it, and the question is, how do I want to parallelize this? And I claim that if we just did the synchronous method that I had on the previous slide, I would be wasting an enormous amount of time if I tried to simulate this particular one, for 2 reasons. So first of all, what's the natural way to parallelize this? Well, if I had 3 processors, then it seems like a good idea would be to each processor would get one of these domains because there's very little possibility of data moving across there. But the thing is that if at each time step, if I look at each vertex and say, what are my neighbors, and update it, I'm not going to be doing very much useful work most of the time. And if I try to, and if at every time step I look at this little narrow inflow and say, is somebody there, is somebody there, is somebody there, that's also a big waste of time. I really don't want to have to do anything until there's an event, until something arrives, and so that gives me something to do. So the question is, how do I organize my simulation to only do as little work as necessary? So as I said, the synchronous one wastes time. And so what I'm going to do instead is something called asynchronous or event-driven simulation. I'm only going to do something when an event arrives, say, from another processor. So there's no global time steps anymore. But instead, every little event who arrives is going to come stamped with a time step. So in other words, if this guy happens to wander off and show up there, he's going to be labeled with the time that he arrived. So he's going to keep track of that. So when I look at him, I don't have to, I know when it arrived. So the example I just showed you, loosely connected pawns. So another example, maybe a little more realistic, is circuit simulation, where you have delays in the circuit, and there may be parts of the circuit which are idle. They don't change for a while until something shows up, and then your functional unit has to turn on. And you don't know when it's going to arrive because of the delays in the circuit. Another example is traffic simulation. You may have each lane going along, and there are certain events that occur when something gets expensive, which are cars changing lanes. You don't want to do that simulation until the car actually changes the lane. So this can be much more efficient, as I've given you the hint, but it can also be a lot harder to parallelize. So the question is, how do you know when an event occurs? So if I'm doing this in a distributed memory machine, clearly I'm going to, I would do a receive. So the question is, when do I know that something has arrived? And so there's, if I do a receive and wait, then I'm stuck and I haven't made any progress. So there's two techniques that people use, and no one is best, to get around this. One of them is called conservative, and the other one is called speculative. And in the conservative approach, what you do is you only simulate up to and including the minimum timestamp of all the inputs. So if all the inputs are good up to time 10, you know that you're okay to simulate up to time 10, and then take one more, because all the information is correct. You can't go to time step 11 because something may change, but you can go up to time step 10. Now the trouble with that is you can have deadlocks, and I'll show you an example on the next slide. So you need to have a way to detect that you've gotten into a cycle of everybody's waiting for their neighbor and get out of it. But people do this in practice, so there's the PTHOR circuit simulator. So the other way to do it is called speculative. And basically you simply bet that you can go ahead and that things aren't going to change. And now what happens if they do? So you simulate up to time step 11, and then something goes wrong and you get an input that's time stamped at 10. You have to back up. And so the extra cost that you incur here is you have to keep some copies of your state at an old time step so that you can back up if necessary and simulate forward if something arrives later than you would have hoped it arrived. And there's other simulators for circuits that do it this way too. So both of these have the following challenge. One of them is that optimizing load balance in locality is difficult. They conflict with one another. So remember, so suppose you have a part of the circuit that's very busy. All the parts are sending one another signals. It's busy computing something. And so that means you'd want to have all those parts of the circuit on one processor, right? Because they're sending one another data at every time step. So that's very low locality, so you want to put them all together. That would give you really bad load balance. If that part of the circuit is very busy, you'd like to parallelize it, but that would then destroy the locality. And so there is no one best way to do it. You have to sort of trade off busyness and locality and load balance. That's just life. Okay, so let me give you an example of this deadlock detection, or why you can have a deadlock, and then what to do about it. How do you fix it? And so I'm going to have an incredibly simple simulation in which, let's say, fish can only swim around the way the arrows go. So I have these three very loosely connected ponds. And so I'm going to do a conservative simulation. And so suppose I've gotten all the ponds simulated up to time t0, but no fish move. So that means no messages are being sent, right? Because there's, nobody's moved. And so nobody can simulate past time t0, right? Because nothing has happened. So everybody just sits there. That's a deadlock. Everybody's waiting for somebody to move forward. So what's the fix? So after you wait for a little while, you send a message to your neighbor saying, are you stuck too? And if you get a message saying, are you stuck too, you pass it on to your neighbor. And finally, if it comes around, if there actually is a cycle, because you can only have a deadlock if you have a cycle, if you get your own message back that says, are you stuck too, you know you're stuck. In that case, everybody can take a step forward. And now, needless to say, this can be a serial bottleneck if you have to do this to take every time step. But if it doesn't happen very often, and in some simulation situations it doesn't, then this is a good way to do it. Okay, So that's kind of the standard, all the standard ways of simulating discrete event systems. And so just to summarize, the model of the world is discrete, both time and space are discrete. And how do we parallelize it? We're going to use domain decomposition, divide up all the points to be simulated into parts, and we're going to try to do that to minimize the surface to volume ratio according to those kind of graph partitioning problems I told you about. And once we've done that, we have to decide, am I going to do a synchronous simulation, time steps, which may make sense if you're simulating a computer and there's a natural clock. Or I may do it asynchronously. That's when I only want to bother doing some work when an event occurs. And in that, I'm only going to communicate on demand. And in that case, I have to decide between the conservative scheduling. I'm only going to simulate up to when I know I can correctly go and deal with deadlocks when they occur. Or I can be speculative and assume that I can just go ahead and be ready to roll back if necessary by keeping some old data. And so I think that's a good place to stop. And the next time we'll talk about particle systems. Are there any questions?